Hi everybody, I hope you guys are having a wonderful day. So in this video, we're going to talk about trees and spanning trees. So trees are special types of graphs, and spanning trees are a certain type of subgraph. So go ahead and take 3 deep breaths, and let's make this math easy. All right, so the definition of a tree has 2 parts to it. So a tree is a connected graph, which remember that means that between any 2 vertices in the graph, there's a path that exists between those 2 vertices. And then it's specifically a connected graph that does not contain any circuits. So this graph here is a tree because if we look at it, all of the vertices are connected to each other, meaning that you could get to the vertices by going on a path through the edges. So it is a connected graph, and there are no circuits in this graph. So there's no way that I could start at a vertex and go through the graph by following along the edges and get back to that same vertex. And so that means that this graph is a tree. And the reason that they call this type of graph a tree is because if you were to arrange the vertices in a specific way, it would kind of look like a tree. So say, for example, that I rearrange the placement of the vertices, and let's say I put vertex E right here, and then I have that attached to vertex A, and then I have E attached to vertex C, and then I have it attached to vertex D, and then D is attached to vertex B, or is adjacent to. You can see, like, with this way of drawing it, it kind of looks like the branches of a tree. And so that's why they call this type of graph a tree. So to practice this, why don't you guys pause this video and determine whether or not this graph is a tree. All right, so on this one, this graph is a tree because first of all, we need to check and see if it's connected. So if I look at all of the different paths that I could take, it looks like all of the vertices are connected to each other. So it meets the requirement of being connected, and there are also no cycles or circuits in this graph. And so that means that this would be a tree. And again, if you wanted to kind of rearrange the vertices, you could make it look like a tree with branches. Because I could say, like, okay, well, here's vertex F, and vertex F is adjacent to vertex A, vertex B, and vertex D, it looks like. Those are all of the vertices that it's adjacent to. And then vertex D is adjacent to vertex G, which is adjacent to vertex E, and A is adjacent to C. And so you can see, like, if I rearranged where the vertices were located, the graph would kind of look like a tree, which again is why they call it a tree. So let's practice that again. Pause this video and determine whether this graph is a tree or not. All right, so this graph is not a tree because this graph is not connected. So each of these individual parts of the graph are trees because there's no cycles in it, but the graph as a whole is not a tree because the graph is not connected. So this would be not a tree. Okay, let's go ahead and try this one. So pause the video, determine whether or not this graph is a tree, and then restart it. So this graph is a tree because let's say I start at vertex E and go to G and F and A, or I could go F to B to C to D and H. All of the vertices are connected, and so that means that it meets the requirement of being connected, and there are no cycles in the graph. It might kind of look like maybe there's a cycle in like this part of the graph because there's a lot of overlapping. But if you were to rearrange where the vertices were located, you wouldn't have that same overlapping because the overlapping isn't actually creating a cycle. It just happens to be where the vertices are located. So like if I were to maybe have F be right here and then have G and then E branching off of vertex G, and then F went to A, and F also is attached or adjacent to B, and then B is adjacent to C, and that's adjacent to D, and D is adjacent to H. You can see like if I rearranged where the vertices were located, you wouldn't have any cycles in the graph. So that means that this graph is a tree. So go ahead and take a look at this one and determine whether or not it's a tree, and then restart the video to see the answer. So in this graph, the graph is connected because I can get from any vertex to any other vertex by like walking along the edges. However, this is not a tree because remember, trees have to be connected and there has to be no circuits. And there is a circuit in this graph because let's say I start at vertex C. If I go C to E to G to D to F to A, I can get back to vertex C. And so that means that there's a circuit in this graph, which makes this graph not a tree. So the second part of this video is the definition of a spanning tree. So a spanning tree of a graph is a subgraph that's a tree and contains all of the vertices of the original graph. So remember, a subgraph is basically like parts of the original graph. So a spanning tree of a graph is basically a subgraph that's a tree, which is why it's called a spanning tree. And the spanning part means that the subgraph has to include all of the vertices of the original graph. So in this picture, the gray part of the graph is showing the original graph, and the black part is showing a spanning tree of that graph. Because if you look at that black part, the black part connects all of the vertices. So you have all of the vertices of the original graph, and it's a connected graph, and there are no cycles in the spanning tree part. Now, notice that the original graph has lots of cycles in it. So the original graph doesn't have to be a tree, but a spanning tree of a graph is basically part of the graph that forms a tree. And most connected graphs are going to have more than one spanning tree. So let's say, for example, that this blue graph was the original graph, and you can see this graph is not a tree because there are lots of cycles in it. But we could find spanning trees of this graph. And so one spanning tree we could have is we could have this vertex attached here and here and here, which is designated with this graph here. And that is a tree, and it includes all of the original vertices. And so that would be a spanning tree of the graph. But you could also have a different spanning tree. For example, you could have this vertex adjacent to this one, and this, which is represented here, and that would also be a spanning tree because the subgraph that I highlighted in red is a tree and it includes all of the original vertices. So spanning trees have to be a tree, so it's a subgraph that's a tree, and you have to make sure you include all of the vertices of the graph. So for example, let me show you one that would not be a spanning tree. If I made a subgraph that looked like this would be a tree because there are no cycles. However, it's not a spanning tree because this subgraph didn't include all of the vertices of the original graph. So spanning trees have to include all of the original vertices, and then you keep some of the edges that form a tree. So to practice this, we could draw a spanning tree on this graph here. So remember, the two qualifications for a subgraph to be a spanning tree is that you have to include all of the vertices, and the subgraph has to be a tree, which means that everything is connected and there are no cycles in the subgraph. So to practice this, we could draw a spanning tree on this graph. So this original graph is definitely not a tree because there's lots of cycles in it, but we can draw a spanning tree on it. So maybe I might say, okay, well, a spanning tree has to attach all of the vertices in the original graph. So my spanning tree is going to include all of the original vertices. And then these vertices need to all be connected, but without any cycles. So maybe I might say, okay, well, let's just make this really easy and connect all of the vertices to this center one. But then I also need to attach these top and bottom vertices, so I could attach them like this. So this would be an example of a spanning tree because all of the original vertices are included in the subgraph, and all of those vertices are connected and there's no cycles, and so the subgraph is a tree. So those are the definitions of trees and spanning trees, and that's it for our video. So I hope you guys have a good day.